Hello guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. We're looking at a Carnot cycle, 1, 2, 3, 4, back to 1. And in this Carnot cycle, you guys know that a Carnot cycle is an ideal cycle. What we know about it is we know the upper reservoir temperature, we know its efficiency, it's 60% efficient, and we know it's receiving 630 kilojoules in the heat addition process. Now, with only this information, we are to find everything else about this Carnot cycle. So let's read problem statement. A Carnot cycle operating with air as the working fluid receives 630 kilojoules of heat at 510 degrees Celsius and has a thermal efficiency of 0.6. A. Show the Carnot cycle on a PV field. B. Calculate the work done during the isothermal heat addition process, the temperature at which heat is rejected, the ratio of expansion by volume in the isentropic expansion process, the ratio of compression by pressure in the isentropic compression process, the work per unit mass in the isentropic expansion and compression processes, the work output of the cycle, the heat rejected per cycle, and then we are to compare the changes in efficiency caused by raising the high reservoir by 100 Kelvin and lowering the low reservoir by 100 Kelvin. And then what do we conclude? So this is a very long question. I'm actually going to separate this into another video, so I'm going to do this on a second part. So that this is not too long, but know that pretty much what we need to do is pretty much solve this cycle for every single thing, right? Every single part of the cycle, only knowing these 3 bits of information here. The thermal efficiency, how much heat is being received, and what is the upper reservoir. Okay, so let's start by showing this on the PV field. We actually had the drawing up there, but let's do it from scratch. We're going to start by doing the 2 isotherms. We know that the Carnot cycle has 2 isotherms, 1 expansion and 1 compression, and 2 isentropic transformations, right? Adiabatic and isentropic, 1 compression and 1 expansion. So I'm going to start by drawing the isotherms. Remember that the isotherms are hyperbolas because P and V are constant, right? P times V is constant, I should say. So let's draw them like so. And hyperbolas, they are always trying to get as close as they can to the axis, so something like this. And the upper one, we know it's 540, right? And then we know that we're starting at some point here, should be good enough, and we're having an expansion. So this is expanding along this dotted line because it's all on the same temperature, right? And then once it finished expanding, so this would be my second point, then we're going to continue the expansion, but now on an isentropic transformation as opposed to a isothermal transformation, right? So continue to expand and increase our volume. Then we start the compression processes. One of them is going to be along this line here, the dotted line, again, because this is an isothermal process. And then we stop somewhere here, and then we go and we have a bit more of a compression, but now isentropic compression, right? So something like, oops, it was too much. So something like this. Okay, so we're going on this direction. And we have state 1, I'm going to call it 1, I'm going to call this one state 2, state 3 down here, and then state 4 down here too. Okay, we know that the energy going, this is the heat addition process, right? This is where Q goes in. So this is where Q goes in, and we know this amount of energy is 630 kilojoules. We also know the temperature of this upper limit here. This upper limit here, we know the temperature for the upper limit, and that was given as 540 degrees Celsius. And we also know the efficiency, right? So the efficiency of this guy is 60%. And that's pretty much everything we know. Okay, so this is the PV diagram. We can put values, if we find values, we can put values for V and P later, but for now, that's all we know. That's the best we can do. Part B, 1. What is the work done during the isothermal heating process? Okay, so know that there's only one isothermal heating process. There are 2 isothermal transformations. This one here is an isothermal transformation, this one too. Okay, but on this one here, we have the heating process because we're giving energy to the system, we're giving energy in the form of heat. And on this one here, we have the heat rejection process, right? So the heat addition process can only be from 1 to 2. So it wants to know B1 wants to know what is work as we go from 1 to 2. That's the question. Okay, and we know that work from 1 to 2, we could go ahead and do work from 1 to 2 is just the integral as we go from 1 to 2 of P dV. That will be fine. However, we don't know P or V, right? So that doesn't really help us out. What we do know is that this is air. We're using air. This is something that I should have highlighted before, but using air, let me go ahead and put air inside this guy here so that we are always remembering that this is working with air. Great drawing skills. Okay, because this is air, let's do this. Because air can be approximated to an ideal gas, then we know that we know that our delta U will be 0. Why? Because we know that on ideal gases, delta U is a function only of temperature as opposed to temperature and pressure, which is the case for things that are not ideal gases, right? So if that's true, then remember that CV is just how du is varying with T. Okay? So therefore, and if we integrate this and our CV is considered a constant, then we're going to have CV delta T equals delta U, right? And if delta T is 0, and delta T is 0 because it's an isotherm, boom. So that means that this guy has to be 0. Okay, so only because this is an ideal gas, we're dealing with air. Okay, so where does that leave us? Well, it leaves us with the following. If we know the first law tells us that delta U equals heat minus plus or minus work, and we just found out that delta U 0, then that means that 0 has to be equal to Q minus work, and therefore Q has to be equal to work. Okay, so in other words, what this is saying, okay, in spite of this being a mathematical way of saying it, but what this is saying in a practical manner is that all the energy that I'm giving to the system, all this Q that's going in here, is being used by the gas, by the air, to expand, right? All the energy being given to the system in the form of heat is being converted into work that's being used to increase the volume of air. So that's where this expansion comes from, right? So we're going from 1, so we're at this point here on the volume axis, and we end up on this point here. So all the energy is being used for that. Okay, so in other words, what is that? So that means that, okay, so if work equals Q, then work from 1 to 2 has to be the same as energy be given from 1 to 2, which we know to be 630. Okay, so this is work that the air is absorbing to be able to expand. Cool, next part. This is done. B2, the temperature at which heat is rejected. Okay, so again, this is an ideal cycle. This is a Carnot cycle. And we know that because we are dealing with an ideal gas, right? Because we're dealing with an ideal gas, and our Cp is considered to be constant, then we know that there's a relationship between the two reservoirs, which is similar to the relationship between the two heat, right? Let's write that down. So that's more. I'm not just saying things, we're actually putting them down. So we know that the efficiency of any cycle will be how much work we can get out of it, heat cycle, right? Divided by how much we have to put in. Right? So how much we pay for it and how much we get out of it. Okay? And we know that we can, because for the first law, we can transform this into, this is just 1 over Q out divided by Q in. Right? But because, and only because this is an ideal gas, and our Cp is kept constant, ideal gas and constant Cp and Cv, then this is also equal to, let's rewrite this, so then the efficiency is also equal to 1 over T over T. Which one is which? Well, this one here we want it to be high, and this is low. In Kelvin, by the way, right? In Kelvin. All right, so we know the upper one. We know that this guy here is, what was it, 540 Celsius. We know that this guy here is 60%. So the only unknown here is the lower reservoir, which is exactly what we're looking for in this question on 2b, right? So we can do 0.6 to be equal to 1 minus T low, which we don't know, divided by T high, which is 540, plus 273, because we need this to be in Kelvin and not in Celsius. Right, so therefore, my T low will be 0.4 times 813 Kelvin, and that is 325.4 Kelvin. And that's our lower reservoir. Okay, now a couple of things that we need to understand, 0.2, not 0.4, sorry. Now, a couple of things we need to understand about what we just did here, okay? So we were able to do this because we're talking about a Carnot cycle. And we know a Carnot cycle operates between two limits, and these two limits are the limits of the upper and the lower reservoir, okay? In addition to that, we know that this is we're considering air, and air can be approximated to an ideal gas. So because of all these considerations, then we can say that the efficiency is also equal to 1 minus the Q out over Q in, which is, in this case, particular, same thing as low reservoir over high reservoir. Okay, so we just found out that because of all these considerations and because of all of this being a Carnot cycle, then this guy here, the lower one, let's put it down here. Where is it here? So this guy here, the lower one, is 325.2 Kelvin, and this one here, we already knew. Okay, cool. Let's go to the next part. The ratio of expansion by volume and the isentropic expansion process. So it wants to know volume over volume for a given part of the process. It wants the isentropic expansion. Isentropic expansion. Well, there's only two expansions. There's from 1 to 2 expansion and from 2 to 3. From 1 to 2 is isothermal, and from 2 to 3 isentropic. So it wants 2 to 3. Okay, so in other words, that question is asking us, what is V2 over V3? Let's put down here B1, 2, 3. It's asking us, what is V3 or V2 over V3? Doesn't matter. V3 over V2. What is this ratio here? Cool. What do we need to do to be able to solve this? We know this is isentropic. So because isentropic, if it's isentropic, then it means that PV to the K is a constant value, right? Constant. Okay, that's what the isentropic ends up doing with the system, right? The pressure at any given state times its volume to the K. K is a ratio between Cp and Cv. For the gas, in this case for air, is always a constant, right? So if that's true, then we can write this as, okay, so that means that P2 V2 to the K equals P3 V3 to the K, right? And if that's true, then what we can do is, because it's an ideal gas, so that means that we can sub in, where we have pressure, we can sub in by P equals mRT over V, right? Ideal gas equation. So where I have P, I'm going to substitute this. So I'm going to be left with mass times R times T2 divided by V2 times V2 to the K equals mass R T3 V3 to the K divided by V3. Note that mass is the same regardless. We're not losing any air in the cycle. R is the same. So now we can build a relationship between the volumes and the pressures. Sorry, and the temperatures, right? We have V to the 1 here. There's a 1 over here, so that's going to be K minus 1, right? We can eliminate this and have K minus 1. So this turns out to be the ratio of V3 over V2 to the K minus 1 is equal to the ratio of T2 over T3. We know the ratio between T2 and T3. What we don't know is the ratio between the volumes, which is exactly what we're looking for, right? Because we know the upper reservoir, which is this guy here, is 540 Celsius, which is the same thing as 813 Kelvin. And we know that this guy is the one we just found, the lower reservoir, which is 325.2. Okay, so what are we saying? We're saying that the ratio between V3 and V2, which is what we want, will just be the, this is 1.4 minus 1 is 0.4, so 0.4 root of 813 divided by 325.2, both in Kelvin, so that we have a ratio. There's no unit to the ratio, right? I mentioned this. So this is 9.88. Okay, so what we're saying here is that, just go back to our PV diagram, 9.88. We're saying that as we go from this guy here to this guy here, this difference in volume here is 9.88 times the original volume. So right, so for instance, if this is 1 meters cubed, then this one here is 9.88 meters cubed. Right, that's what we're saying. That's what we just found. Oops, that's just going to stay there. Cool. So that's that. Next one. This is done. The ratio of compression by pressure in the isentropic compression process. So now it's the other isentropic one, and then what's the ratio between pressures? So which are the isentropics? This is the one isentropic, this is the other isentropic, right? It's asking us in the compression. So this is an expansion, this is the compression. What is the question? What is the ratio between the pressures? So what is P1 over P4 or P4 over P1? We know P1 is greater, right? You can see just by looking at the graph. The pressure is greater on 1 than 4. So it makes more sense to do P1 over P4 and find this ratio here. Okay, so this is B4. B4. And we're looking for the ratio between P1 and P4. So what is this ratio here? Well, we're going to do exactly what we just did before, right? Because same thing, it's an isentropic transformation. So because isentropic, delta S equals 0, then P1 V1 to the K has to be equal to P4 V4 to the K. In this case, we want P1 over P4. So that's really very straightforward, right? We want P1 over P4. That ratio there is going to be just V4 over V1 to the K, which for the case of air is 1.4. Right, so very straightforward. We know the two pressures. Sorry, we don't know the pressures. That's what we're looking for, but we don't know the volumes either. Right, all we know is the ratio between the two temperatures. So this is not going to be good enough. We're actually going to have to do the same thing as we did before, where I have volume instead of leaving that as volume. What I'm going to do is I'm going to sub in volume equals mass RT divided by pressure. And so I'm going to have P1 mRT1 divided by pressure 1, and this is all to the K. And over here I'm going to have P4, and then mass RT4, P4, and this is also 2 to the K. So in this case here, they're all m to the K, r to the K, they're the same on both sides. What we need to be wary of is the temperatures, right? So we have the temperature ratios to be able to get rid of the pressure ratios. So what I'll do is I'll send dividing pressure over there. So we're going to have here, so this is the same thing as P1 to 1 minus K, and minus K because we have P dividing there to the K, is equal to times T1 to the K equals P4, 1 minus K to the T4, and therefore P1 over P4, which is what we want, to the 1 minus K equals T4 over T1 to the K. Okay, so we can take the square root of this, so we can have what we're looking for. So P1 over P4 will be just the ratio between temperatures to the K, 1 minus K. Again, we know this T4 is the lower reservoir, so 325.2 Kelvin. T1 is the upper reservoir, 813 Kelvin. And this is 1.4 divided by 1.4 minus 1, so negative 0.4. And this is about 24.7 approximately. That's the answer for this part there. Okay, so again, what is it saying? It's saying that the pressure on the first state is 24.7 times greater than the pressure on the fourth state. Okay, so as we're going from this guy here to this guy here, one is 24 times the other. So if this is 1 atmosphere, then this guy here is 24.7 atmospheres. Right, that's what we just found out. Brilliant. What's next? Next part of the problem. Oops, wrong way. So this is done. The work per unit mass in the isentropic expansion and compression processes. So the isentropic ones are the ones we just looked at. We know a lot about them already, and we're trying to find the work per unit mass. Okay, so this is B5, B5. We want work, and we know work is integral of PV from A to B, right? So for any two states we want to go. Now, in the case of the isentropic ones, we know that the integration is going to be very similar to the integration on the polytropic process, right? Because again, PV to the K is a constant. Okay, so we can go back on videos in which we did this integration. What we're doing is we're subbing, when we have P, we're going to sub in constant divided by V to the K, and that's going to turn out as so. Work will be P of the final state, so let's put P of B, V of B, P of A, V of A, divided by K minus 1. Okay, I'm not going to integrate now. I'm going to skip that, but you can go back on the video that we did that and check it out if you're not sure. Okay, so we can do that. That's one of the ways to do it. But then what's the problem? We don't know the pressure or the volume, right? And we don't know the pressure or the volume on any of the states. So that doesn't really help us out in here. What we have to do is something similar to what we did on the first part on B1, right? On B1, we're trying to find the work, and we had to relate to the ideal gas situation in delta U. So again, we're going to do the same thing. We're going to take advantage of the same thing. What's happening on the isentropic processes? We know that the isentropic processes, these guys here, this fella here, and this fella here, they're isentropic and adiabatic, right? If they're adiabatic, what is that saying? It's saying that the Q, as we go from 2 to 3, and as we go from 4 to 1, has to be 0. There's no heat entering or leaving the system during our isentropic processes, right? So if that's the case, then we can apply the first law of thermodynamics, because that's just going to be our way out, because we don't have the information that we need, right, to be able to calculate this way. So because, let's put it this way, because adiabatic, and remember this is adiabatic just because it's a Carnot cycle, right? It's the only way we know. Then Q equals 0. And if Q equals 0, and we know delta U will just be heat and work, and this guy goes to 0, then delta U just equals work. It can be negative work or work, depends on the type of sign that you use. But the idea here is that any change, the quantity, right, the quantity of energy is going to be the same. However, delta U changes is the amount that's going to be changing in terms of work. And we can find delta U quite easily because this is an ideal gas, right? So again, same thing we talked about before. CV is a derivative of how du changes to T. And in this case here, we can do we can integrate for the whole thing, and we're going to be left with CV delta T equals delta U. And this can be, we can do that when it's an ideal gas and when this guy here is not changing with temperature, when this is considered constant. Okay, so that leaves us with, okay, so it means that work, we can do first from 2 to 3. Work from 2 to 3 will just be equal to how delta U is changing from 2 to 3, because it's adiabatic and heat is 0. So then that means that we can just put the CV, which is for gases, for air I should say, is about 0.718, and the difference in temperature. So what is T3 minus T2? Oh, there's the negative, right? Keep the negative on, so there's no dramas. This is the lower reservoir, this is the upper reservoir, so we're going to be left with 0.718, 325.2 minus 813. Unit-wise, we have kilojoules per kilograms Kelvin, unit for CV, and we're multiplying that by Kelvin. So we'll be left with energy per unit mass, which is exactly what the question is asking us to find. Negative sign to the other side. This is going to give me that from 2 to 3, we require 350.24 kilojoules per kilogram. Okay, so this is an expansion, right? That's why our work is positive here. That's why we're getting a positive number, because the air requires this energy. It uses this energy to be able to expand from 2 to 3. So when it goes, where are we? Here. When it goes from this volume to this volume here, it requires energy, and that energy is being given in the form of the lowering of the delta U. So delta U is lowering, so that it's giving energy to in the form of work for it to expand, right? So it's lowering its, because it's an ideal gas, so it's lowering its temperature to be able to expand its volume. That's what it's doing. Okay, and then because this is a Carnot cycle, then we know that on the other side it has to be exactly the same, or else it's not going to be the ideal situation, right? So we're going to do this again, obviously for 4 to 1, but we need to find exactly the opposite, the same amount of energy, but because of the compression, something that's going to be absorbed, right? So it has to be 350 on the other side. But that's quite obvious, right? Because again, work as we go from 4 to 1 has to be equal to delta U as we go from 4 to 1, because it's adiabatic. In this case here, it's going to be CV, and then T of 1 minus T of 4. And you can see everything is exactly the same, because T1 is the same as T2, and T4 is the same as T3. Right? So this is a higher one. This is the 813, and this is the 325. Okay, so that's, we're saying that negative, right? Negative. 4 to 1 is just 813 minus 325.2. So this is going to give me a positive number, multiply by positive number, and then because we have the negative there, the whole thing is going to be negative. Okay, so this means that work from 4 to 1 is equal to negative 350.24 kilojoules per kilograms. Okay, again, same thing. Why is it negative? Well, because it's now compressing. It's decreasing in volume, so it has to output this energy somewhere, right? The energy cannot be destroyed. And because the energy cannot leave in the form of heat, because it's adiabatic, then the only place it can go is as internal energy for the gas. So its internal energy increases in detriment to its volume that is decreasing. Cool. Is that it? Or do we have another one to go? Oh no, still have 2 more to go. The work output of the cycle and the heat rejected in the cycle. Okay, cool. Work output of the cycle. This is B. I think this is B6. I'm losing track already. So what is the work output? Well, the work output is going to be the surplus of energy, put it that way, as we go around the cycle once, right? So we can go back. Let me copy the cycle. It's probably the best. Let's get rid of the things that we're not interested in here. Okay, so let me get rid of this for now. Okay, so as I go from 1 to 3, okay, as I go from 1 to 3, I'm going to be expanding and therefore requiring that amount of energy, right? The area under the curve. As I go back from 3 to 4, I'm going to need this amount of energy here, the blue one. And from 4 to 1, I'm going to need this amount of energy here. The difference between the two is the amount of energy that's being outputted, which is precisely the area inside the cycle, right? So it's the difference between the two areas. So there's a couple of ways we can do this, but the easiest way, because it's a cycle, is to know the following. if we're going from 1 around the whole thing back to 1, then my delta U has to be 0, right? Because we're doing, the initial one is the delta U on state 1, and the final one is delta U on state 1. So U1 minus U1 is 0, because this is a property state, right? So the property state has to be the same regardless of which way you went or how you came back. But if that's true, then we can find out what is the useful work out of this, because we also know the efficiency, right? The efficiency is how much work we got out of this thing, useful work we got out of it, divided by how much we had to put in, how much we had to pay. In this case, with useful energy, with the high quality energy from the high reservoir. We know that this is a 60% efficient engine, and we know that we're giving it 630 kilojoules. So that is very straightforward, right? The amount of work that I can output from this cycle will just be how much I'm putting in times how efficient it is. If it's 100% efficient, I'm getting everything out. That's unfortunately not possible according to the second law of thermodynamics, but that will be the case, at least mathematically speaking. So 630 kilojoules times 0.6, no units there. So my Q out is about 378, and that is kilojoules. Not kilojoules per kilogram, but kilojoules because we're just using the same unit as the heat going in, right? And the last one was the thermal efficiency. No, the heat rejected. So heat rejected. So let's do that here. So this is B, and I think this is 7. I'm going to guess it's 7. And it wants the heat rejection. But then again, remember that we talked about this. What are the energies that are being outputted from this system? We have, if we look at this guy, it's a heat engine like that. Then we have the upper reservoir, so high reservoir. We have the low reservoir. And we know that what's happening with energy here is that we have Q going in like that. We have Q going out like that. This is happening as we go from 1 to 2. This is happening as we go from 3 to 4. And we know that there's a work being outputted. Okay. So because of the first law, right, we do a little energy balance on this guy here, we're going to easily see that Q in has to be equal to work out plus Q out, right? Because we can't create or destroy energy. So if you go back to our concept, that the efficiency is just how much we can get out according to how much we put in, then we can substitute where we have work, we can substitute that by Q in minus Q out. The whole thing is divided by Q in. But this guy divided by this is just 1, so this is the same thing as 1 divided by Q out over Q in. Right? So in other words, the heat rejected and the heat coming from the upper reservoir. So we know everything here, right? We know this is 630 kilojoules. We know this is 60%. The only unknown in this case here is precisely Q out that we're trying to find out. Right? So that means that I can do 1 minus the efficiency will be equal to Q out over Q in, and therefore Q out is just 40% of whatever the 630. $252 kilojoules. Cool. So note that we solved the whole thing. We found a lot of information for the cycle without having much, right? Because the only thing we knew from the start was how much was going in, its efficiency, and the temperature of the upper reservoir. We were only able to do this because this is a Carnot cycle, so there's a lot of things that are ideal here, and because we had the knowledge on how the Carnot cycle operates. So we're considering this to be an ideal gas, constant CPs and CVs, and a Carnot cycle. Because of all this information, then we can approximate things and simplify things and be able to solve like we did. If you don't have an ideal gas, if you're talking about water, for instance, on a Rankine cycle, then you have to be wary of this, right? Don't jump into using the same things; they will not work. Likewise, if you don't have a Carnot cycle and you don't have, for instance, an isentropic transformation, then be wary of this too, because you won't be able to use some of the relationships we did, like this one, for instance. Where is it? Okay, this is only true if it's an isentropic transformation. Okay, there's still the last bit of the question, but I'm going to do that on a separate video, so this is not